Hello, everybody. Welcome to another episode of DE Webcast Series. My name is Kenneth Wong. I'm Senior Editor for DE 24/7. Good morning, good afternoon, good evening, depending on whatever time zone you happen to be joining us. Glad to have you along. Today's episode is called Under the Hood of Easy to Use FEA. FEA meaning Finite Element Analysis, and it is sponsored by CATI, Computer Aided Technology, Siemens, and ComSol. I'd like to thank all our sponsors for making this live discussion possible. First, let me give you a few technical tips so that you get the best experience possible. Before I begin, if you have questions about the topic, even now, for the panelists or for today's topic, you can submit them into the Q&A box at any time. We'll address as many of them as possible, as time permit, after our panel discussion. For the ones that we cannot get to, I promise you we'll work with the panelists to make sure that you get a written response. You can also check out the resources related to the topic to the resource list to the left side of your slide window. If you experience any kind of technical problems, you may want to visit our webcast help guide by clicking on the help ? Icon at the bottom of the console. If the slides are not advancing, try pressing F5 and refresh your browser. That usually solves the visual issues like that. Today's panelists have all agreed to reveal some of the mechanics, some of the tools of the trades behind or under the hood of these easy-to-use FEA applications and simulations to help us understand how they work so that you know what you can and you cannot do and what the limits and what the scopes of these are. So let's meet them one at a time. The first one that I'd like to call to present is Joe. Joe is from CATI. Joe, welcome. Would you give us your self-introduction and opening remarks for 4 minutes, please?
Okay, great. Thanks a lot, Kenneth. I'm assuming, Kenneth, that you can see the screen right now. Hopefully. Yeah, I'm Joe Formicola. I'm going to tell you a little bit about our simulation team here at CATI. I'm heading that group. I've got over 30 years of simulation experience, hands-on. I was mostly working in consulting and doing finite element analysis myself in a consulting environment almost all my life. I started a company called K-Links, which was bought by CATI a couple of years ago. Love working on engineering problems, problem solving, and helping people reach their potential. So our simulation team is, with our sales and engineering, we're about 40 large right now. We have a US-based simulation team, and we do software support and training for Dassault products and for SOLIDWORKS products. As far as our consulting and scope, we go through electromagnetics. We have some experts in that, optimization tools, co-simulation and multiphysics. We'll develop methodologies for a company that they can use over and over again and templatize, as we're going to talk about today, vibration and crash and fluids, and in particular, validating FEA results is something that we think is a key component to our success. So talk a little bit about this as an introduction about Dassault systems today. We have our SolidWorks portfolio, and this kind of leads into, well, how are we going to make things easy, right? So we have experts in SolidWorks, and we have FEA experts in more highly advanced tools like Abacus and PowerFlow and multi-body dynamics and all that. So, but the simulation tools that are inside SolidWorks are really, really fantastic, and they're people, designers, they love having that capability and that the fact that they're inside SolidWorks. So there's structures, there's flow, there's multi-body dynamics, there's injection molding capabilities. It's all highly accessible, as it says here. The thing is, it's all been a little bit more controlled from a general purpose solver so that it's usable by the designer. And it's so there are some limitations, but it's really something that is kind of considered very useful for a designer having it embedded in the CAD. And then there's the Simulia portfolio, which has all the high-end solvers, Abacus and Simpac, and the fluids, electromagnetics, acoustics, all of that stuff. It's very resource intensive. It's usually mostly for analysts. It's not as easy to use. You know, you can make errors easier. You can, but it's comprehensive. You can do just about anything if you use all these tools. So it has a comprehensive capability. So we have those two sides of the coin. So how do we bridge the gap, and how do we start, maybe creating some templates and making it easier for designers to use and make better products? Well, some of the problems are, specialists in simulation, they're a little bit scarce sometimes. You may have some cumbersome workflows, complicated situations that the design team can't do, costly licenses, limited compute power. So all of these are difficulties when trying to bring it be easy to use to the design team. And the solution that Dassault has come up with is the platform, the 3D Experience platform. So it brings all the CAD tools and the simulation tools onto a single platform in such a way that they're going to be much more easy to use for the design team. And that's really kind of the solution from Dassault to bring high-end simulation and design and integrate those together and make it perform better. This is a little example here of a drone sitting sideways. These are some guardrails here, and it's a drop test. It's going through bringing a SOLIDWORKS file into the 3D Experience platform, building up a simulation. And I'm not sure how much time I got on the introduction, so I'll speed this up a little bit. Automatically meshes it, start putting in things like your initial velocities and your directions of drop, and lo and behold, you're starting to do some drop simulation and understanding how your structure will perform in a much more complicated simulation than you would be able to do in SOLIDWORKS. So complex material properties, highly deformable, large displacement, impact, basically as deep as you need to go. You're going to have that power now for the designer as well as the analyst. And Kenneth, I'm gonna hand it over to you now. I'm going to stop sharing, and I hope that was a little bit insightful.
That was very good, particularly the template and the way you are able to see how it works is really helpful. Thank you so much, Joe. So now let me go ahead and call Mark to the table. One moment. Okay, Mark, this is your turn for your self-introduction and your opening remarks for 4 minutes, please, Mark.
All right, thank you, Kenneth. And I am Mark Lamping, and I work for Siemens in support of simulation and SimCenter 3D as an application, and also NX. So simulation truly can be a bottleneck to delivery of products. And with the handoffs between design and simulation departments, disparity in tools and an uncommon language, it's not surprising that simulations cannot keep pace with design milestones. And, this leaves the designers with insufficient feedback from the simulations and potentially making educated guesses in terms of design decisions. In the end, you may not be confident with the final design because you just don't feel like you maybe got enough feedback from simulation. So, let's take a look at Denso as an example. This content is from a presentation that was given at Realize Live in 2022, just this month, in fact. And Denso admits to facing the challenges we are discussing today. First, take a look at the historic or design simulation relationship at Denso. The designers do few CA tasks, but really rely on the CA department to do nearly all of them. Data translation and communication are significant barriers. The CA users perform tasks in tools that are inaccessible or unfamiliar to the designers as well. So this causes some friction, and designers are disappointed because of the long lead times. Getting to a set of results and a report back to design, it takes time, and it could delay part releases and cause engineering changes. Designers also view the CAE feedback as a disruption, if it's delivered late or at a point in time when they're not expecting this feedback. The CAE specialists often view simple tasks that they receive from design as mundane, routine, and uninteresting. Even the simple analyses take time and effort, which takes away from more challenging assignments. And the simple things are vulnerable to miscommunications as well when you're going between departments and between people. When that happens, the CAE cycle just starts all over. Both the designers and the CAE specialists have problems with this historical situation. So, Denso has addressed these difficulties by placing easy-to-use CAE tools in the hands of the designers. Within the design tools of NX, Denso provides designers with CAE templates and guided basic analyses that positively impact the product design in a timely fashion. The integration of the design and simulation tools with NX and SimCenter 3D is really fundamental to Denso's simulation efficiency improvements. And as the graphic shows on the slide, all communication stays within the design department, thus reducing interdepartmental dependencies and delays. So in the summary, Denso identifies a couple key takeaways. Enabling designers to perform standard CAE work, that drastically reduces the time required to sound engineering decisions. Attributing the CAD model for use with a CAE template is a fantastic way to speed up the creation of CAE models, and designers improve their design skills by running CAE themselves. They become part of the solution, and they are a bit better because of that. And that takes care of my introduction. Oh, nope, I have one more slide, sorry. And so if we think about simulation-driven design, and it can help you front-load simulation in your design cycle and shift your development processes further to the left. With simulation-driven design, it's possible for designers working within their CAD environment to actually start the design process by using simulation first. And then this can even influence what the initial design. So, after getting that initial shape, the designer can continuously perform simple qualitative simulations on each design iteration to make sure the design is on the right track and it's meeting the expectations. This helps the designer achieve a more robust part that can be released more quickly than previously based on the old process. And it also frees up your simulation team by reducing the amount of time spent on more routine analyses and lets them focus on more complex analyses. And now I'm finished, Kenneth. So it's back to you.
Summary of the workflow that we typically see. Thank you so much for sharing that with us.
Mm-hmm.
Very good. Now let me call David. David, welcome. This is your time for self-introduction and opening remarks for 4 minutes, please.
You got it, Kenneth. Thanks for that introduction, and thanks for this opportunity. So just a little bit about me. I've been with COMSOL for about 20 years, straight out of UCLA, where I studied numerical analysis for simulation. And so it's been interesting to see how the industry and how the company has developed over that time. Today, though, what I'm here to do is I'm here to talk to you about what COMSOL is all about. What is our goal? Now, you're probably aware that COMSOL is a finite element platform, a simulation platform, and we specialize in multiphysics. We're among the best there, no question. But our goal is not just to stop there, but it's actually a little bit broader than that, and it goes even further. The main thing is that we want to bring simulation and all the benefits of simulation to everyone in the product design workflow, and we believe it's possible, and this is what is our mission, and this is why we call this thing the democratization of simulation. So this is what we mean by this term. This term was actually not created by us, but it's been used out in the by a few journalists first, people like Kenneth, and it's been and I think we like to use it because it really gets across the idea that both the previous speakers talked about. We want to bring simulation to more people, and we also want to clear up that simulation bottleneck. And so with that, that's what we mean by the idea of the democratization of simulation. So to illustrate this, here's a little picture, and here we have a typical simulation-driven product design workflow. So there's 3 pillars, and they represent the 3 different categories of the different people involved. Up at the top here, you have the modeling experts. That's people probably mostly like the audience today, where they would use a product like COMSOL, and they are really good at it, and they're trained at it, and they are the experts. But then there's another category of people, an even bigger category of people, and these are the design engineers. These people who have their priority to be the improvement of a product or a process. And they use simulation, but they also use a lot of other things. But they can definitely benefit from simulation, although they're not trained simulation experts. Then we go all the way down to the factory floor, and these are the people that are putting together the actual product or process that you are designing. These people are critical, and they have a lot of knowledge, but they might not even be interested in simulation at all. But they can still benefit from it, and I think this is what COMSOL is working towards. And so one example of this is, here's a typical example. So here's a example of a COMSOL model, full physics model. So this is something that one of the modeling experts would use. Here you could put in the inputs like physics and in different parameters, the geometry, the mesh. You worry about the outputs, the results, how it's outputted, animations. You might want to do other kind of post-processing. And so it's nice in COMSOL. You have one-click access to any part of the modeling process. You have access to a lot of different types of physics. It's fully compatible. You can mix and match the physics as you like, and it's very, very flexible. But the problem with this is that it might be too flexible for some people, and that is why we have created tools within COMSOL to simplify your model from that full COMSOL model down to a application or a simulation app. And so this is what is shown here. Here we have maybe a much more simple inputs and much more simple outputs. So here's a little example of an app that's created within COMSOL. Now you notice the previous slide had a lot of had a full model tree. There's different settings, all sorts of stuff. That was a full COMSOL desktop. This is a simplified version where you only have access to a few different parameters that you could type in. You have a couple action buttons at the top. You could press $, etc. And eventually you get this beautiful picture. This model, it happens to be a mixer. And so this is something that the design engineers could use. So maybe not people up at the top would be using that, but the people at the design engineers who don't have the full education to do the full model, they would be able to use that. And so to take us all back, this is what the democratization of simulation is all about. That was one example. There are other ways of doing this as well. But the idea is to unleash the power of the modeling experts by giving them access to tools that can get them to propagate their knowledge through simulation and simulation apps and other ways that would go through the entire product design workflow. Everyone from the modeling experts to the design engineers all the way down to the factory floor. And so I think this slide really summarizes it nicely here. So COMSOL Multiphysics is a platform, and it's used to create a team, department, organization, or enterprise. It allows people in the simulation product or process workflow to participate, collaborate, and communicate. So that's what we're working towards, and I think we're making some good steps there, and hopefully today's discussion we can talk about it more.
Very good, David. Thank you so much. All right, so let's start our discussion. I'm going to bring all of the panelists back here so that all of us can have a discussion here. Let me kick it off with Joe. Joe, the first contact for a designer to come in contact with simulation probably is a CAD embedded simulation app. Usually they are linear, they are not too complicated. Could you tell us about in general, do you feel like they serve the CAD user designer level simulation need, and are there pros and cons?
Yeah, let me let me share my screen again here. So as far as I'll just talk about SolidWorks right now. SolidWorks is really kind of it's one of our babies. It's what we work on, and we're the largest reseller of SolidWorks in North America. And so we have 170 engineers at CATI. Most of them are SolidWorks designers, and they're all SolidWorks lovers, right? So the first thing that you can make a SolidWorks designer or design engineer happy with, say, hey, guess what? You can do kinematic studies in SolidWorks. Like, no kidding, great. Is it in SolidWorks? Yes. Oh, then it must be perfect, right? So if it's in the tool, it's great. Doesn't matter what its specific capabilities are necessarily, but from a designer perspective and a SolidWorks user or any type of CAD tool user, if it's right there in the interface and it's directly related to my CAD model, I really feel confident, But there are limitations, even if they do have which plastic optimization, the parametric capability within SolidWorks for simulation is fantastic. It's fast, you get good results, the price is cheap, all that stuff. But as far as what the limitations potentially are, is that they have really good solvers embedded in SolidWorks, but they have been controlled to a certain extent. So there's some higher end stuff that you just cannot do. You can't scale your simulation as much. In particular, there's no dynamic explicit analysis. There is a drop module, not for a crash or a blast, something like that. Some of the higher end material behavior is not there. General contact you can't do. Fluids code is excellent, but there's definite limitation, I would say, are associated with embedded simulation within that tool. That's basically what we're trying to address with 3D.
That makes it very clear the different level of simulation that is possible. Thank you so much. Let me go ahead and call on you, Mark. To make simulation more accessible, obviously there are certain steps in the pre-processing that could be automated, and many are in fact automated now. What are the steps that are automated or pre-configured? Could you maybe give us a rundown of those?
Yes, and let's see, I need to push my slide, is that right? First?
Mm-hmm. Yes.
Okay, so that would be the it jumped on me, I'm sorry. So,
yeah, no problem.
Okay, so
we see it. Here we
go.
go.
What I'm trying to do is tee up a video that I'm going to talk to, but a complete analysis can really be pre-configured in a simulation via a template. But first you have to determine whether or not that analysis is it really something that is standardized and repeatable as part of your processes in your company. And if it is, then that analysis can act as a catalyst to a template. The outcome of that template is a CAE process that you capture from a model that was created the first time without a template. And so let's just have a look here of an example of a template in action. So I'm going to push my video, proper one, to the audience, and this is going to load up, and I will start talking to the video. What we have is a CAD assembly, and we're applying a FEM template to this CAD assembly. So all the meshing is going to be driven by the template and attributes defined in the CAD assembly. So you'll see different solid bodies here, and even some 1D connections being generated between the bodies based on content that's in the template. And then we go ahead and generate a simulation. So, loads, boundary conditions, the solution setup, all of that via another template. And we have a normal mode solution. We go ahead and solve that. So the user only created a FEM from a template, created a simulation from a template, and then he solved the model. He didn't have to do any meshing or any boundary conditions or anything. He gets his result. That again is an item that could be in the template in terms of the formatting of the display. And now we run through the same process again with a different CAD assembly, but it's attributed in a similar way so that it can be leveraged by the templates. And again, you create the FEM template or FEM from the same template as we did before, and you end up being able to do these comparisons from one design iteration to the next. And so then basically you end up with a situation where the templates give you that easy to use FEA for the non-expert. But at the same time, there's no reason why an expert wouldn't want to leverage templates as well, because, nobody likes to go through the drudgery of setting up the model, and they'd rather get to the more interesting parts of, the post-processing and figure out what's really going on. So thank you, Kenneth. And, back to you.
Sense. Yep. Let me go ahead and call on David then. David, I think COMSOL's approach also involves template to make it more accessible simulation. So COMSOL Publisher, for example, is the purpose of that. Could you also tell us about how templates work and pros and cons, if you will?
Sure. We actually don't use the term templates. We actually prefer the term applications. And that is because what we're really doing is you're actually designing a mini software. So in other words, you can actually use, we actually have a tool called COMSOL Compiler that lets you not only create the application, but you also can compile it and distribute it as you'd like. So maybe I could do a quick demonstration of that since you asked. I'll just do a quick screen share if it's all right.
Okay.
All right, so here we have a simple COMSOL model. This is a, come up here. This is a bus bar. And, I don't want to go into too many details. It's a Joule heating model. But basically what I can do is I can take this bus bar and make it into instead of a template, an application. And so to do that, we'll use this thing called the application builder. I click that button, and I can make this app within a minute. I'll take 2 because I have a little bit of time, but I'm just going to create a form here. And this form allows me to select different, this is where we use the word template, to select different templates to create your app. And so I'm going to actually have this template to create a compact layout for a tablet. So yes, you can actually create apps within COMSOL to be run on tablets, for instance. So I'm going to go ahead and make this compact layout for a tablet. You could also do for smartphones, etc. I'm going to choose my menu buttons here. Let's choose a simple one, plot geometry and compute study. Let's also do plot. Let's do plot current density. That's a good one. And then I'm going to go for the inputs. I'm going to have the length of my bus bar as well as the applied voltage, just for fun. As far as an output goes, I'm going to output the, let's output the maximum temperature. We'll do that here. And you can kind of see as I build this, the little preview pops up there as I go on. And I just click done here. And believe it or not, I have created a little mini software. So if I click test application, it'll launch here in just a second. Up pops the app. So this is obviously a much more simplified thing. It has 2 fields to input, and it has a field there to output. I'm going to go ahead and just press the geometry button. Here's our default. Let's go ahead and let's go ahead and increase this to maybe, that's too many. Let's go to 15. So I make this longer one here, like that. And let's leave the applied voltage. I press the compute button, so it's going to go through the process of solving. You'll actually see little progress bar in the lower right corner pop up. This is all, so underneath the hood, this is actually the full COMSOL model. But the front-end user interface has been created by the modeling expert to strip away all the non-important things and let the user focus on the important inputs. And so the computation is done. I click plot current density, and here's the current density. So just like that, I've created an app. And like I said, you can actually use the COMSOL compiler to then package this and then distribute it as you like. You can actually let people run it even without a COMSOL license. So this is one example of, like I said, we don't call these templates, but they're the apps. And anyway, it shows you how that can be done. All right, so I'll go ahead and stop the screen share here. And yeah, so hopefully that gives everyone an idea of how that's created. Oh, one other thing I should mention, the application builder itself, in other words, the front end UI design tool is actually built into the core COMSOL multiphysics. You don't have to buy anything else. So we really feel like it's an important part of the design process and is actually fundamental to the simulation process. So we've actually included that with our core package as well.
Wonderful. It's good to see all the different approaches to easy, accessible simulation. So now let's get a little deeper into it. I'm going to call Joe back to the discussion. Joe, are all CAT embedded simulations created equal? Are all templates created equal? Should they be, depending on who they target? What are your thoughts on that?
Okay, let me screen share again for you. I have an answer to that.
Okay.
So the idea is, we're talking about templates or we're talking about apps. What are we really talking about, right? Are we talking about automating a process or coming up with a solution that is repeatable over and over again? So there's a couple of different levels. The first that we have in 3D Experience and in SOLIDWORKS is our simulation wizard or assistance that will go through the step-by-step process of to make sure that whoever's using it isn't missing a step and can get a green light next. So that's basically one form of template that's very important to make sure that people who aren't really simulation experts can make sure that they don't miss a step. It's good if you're trying to do something and get a specific result and walk through that yourself. Someone else might not use it after you use it. It'll always run through every time. So that's one method, right? Simulation wizard. They're very robust, and it depends on what type of physics you're solving, but it'll walk through you if you're integration or heat transfer or whatever type of physics it is. It'll make sure that you get all the right things into a model so that it run. Doesn't necessarily mean that you've set up the model you want. And then that's where what we have in 3D Experience are called engineering templates. So they're engineering templates. They're called simulation templates. They're developed by an expert analyst who has the capability of validating these methods, integrated in with physical testing, make sure that they're correct, usable. A lot of what 3D Experience calls it is methods developer type analyst. And these engineering templates are incredibly robust. They can be created on very abstract geometries, and then you can put in the complex geometry as you see here, so that you can basically solve whatever you need to solve. So this is how we integrate the CAD and the simulation together, is through a simulation engineering template, and it's available on the platform, and it's fully functional, and it was one of the key components to developing the platform. The other piece is, I'm sorry, am I over time here?
No, I'll just say
one of the very important aspects of it is parametric. So setting up processes and which can put together detailed results and various parameters that you can run thousands of test cases and look at all the results. And when you put parametric optimization and a design study into your simulation template, you've got some incredible there. So I'll leave it at that. I was going to talk a little bit about generative design too. Some people call that a template in a way because it's creating a shape for you automatically after you put in the boundary condition. But anyway, so those are what we consider like 4 different things available.
Very good. We might be able to come back to the generative design question a little bit later. Thank you very much. For now, Mark, with the template-driven approach, you will call it template, and David likes to call it application, right? With the template-driven approach, how do you control the parameters input so that somebody wouldn't, for example, try to put in 80 miles per hour for a template that is designed to analyze 60 miles per hour vehicles or something like that? How do you control the scope?
Right. So again, I'll push my slide to the viewers, and the templates and standard features of the product really take care of much of that for the user. So an example of a standard feature would be if a material is assigned to a body in the CAD, the CAE model, the meshes generated on that body, inherit that material. For shell thicknesses, if you define that shell mesh on a mid-surface geometry, we go and evaluate the shell thickness from the solid body. So that's kind of out-of-the-box capabilities that would be part of a standard product. And then templates, they certainly would leverage that information, but they also have the ability to define meshes individually, and all of our UI, so our dialogues in the context of meshing, would be essentially captured in the template as the user filled it out. So you imagine, the expert user filling out the definition of how the meshes should be defined, how materials, thicknesses, beam cross-section properties, spring stiffnesses, and so on. Those are all captured, in the template. And really, a template is just a completed CAE model from a previous project with new CAD associations to it. In terms of solutions, a template can contain any of the supported solutions among the solvers supported by SimCenter 3D. So a template is, equally applicable to a linear static solution as it is to a thermomechanical transient analysis. Magnitudes of loads, temperatures, solution steps, and so on are all critical pieces of knowledge that exist in the template. So I want to play a video that shows the basics of a template. So this is a cartoon model, and it's supposed to represent an analysis of a battery bracket. So I've got a lump mass in here for the battery itself, and you can see that the mass is kind of hard-coded in there in the properties table. And that mass is defined on a point, and we identify that point in the model by attributes defined in the CAD model. That point is connected to a face, and so the load of the battery would be distributed to a face or even a set of faces, and those sets of faces would be identified by an attribute on the CAD. Here we're showing the definition of a spider element to distribute it from a point to a face, and then we see here the face attributes that we are looking for to connect that point to. And then we see that particular face that is highlighted there has the attribute that we were looking for that connection. And then we go into the solid meshing dialog, and all those settings in that mesh dialog are captured by the template. And then we're going to go into the simulation and take a look at, and have a solution set up. It's a linear static solution using the SimCenter Nastran solver. It has 3 subcases. Loads are already defined, and so the magnitudes of the loads are defined, and so that gets to your point, Kenneth, about potential user error. if you're running a standard analysis, standard load cases, those are already predefined for you. Constraints and things like glue and contact can also be addressed too in the template.
Wonderful. That's a very good idea to sort of control it at the input level. David, same question, but I would refer to it as application in your case. So how do you control in the application that people don't use the turbulence model or the physics that is it is not designed for that purpose?
Yeah, great question. So let me, I'm not going to do a screen share, but let me go ahead and put a couple of slides here. So this is the COMSOL desktop, and this is involved, right? It's got this whole entire outline here. You can add any physics that you want. You can change your turbulence model, as you mentioned, and you can type in anything you want into the settings window, imaginary numbers if you really felt like it, and you'll get the corresponding results, if it converges. And so you have full flexibility, full access here to everything. Now, a novice might actually do something like that, and they put something ridiculous in there and get some garbage in, garbage out answer. And so what we like to do, and what we've empowered people to do, is something called the application builder, and that's this little tool, and it's actually installed with your COMSOL multiphysics software. If you actually, I'll go back a slide. If you look in the upper left corner here, there's that big capital letter A that actually takes you into the application builder. So it's a built-in tool, and it's a front-end user interface design tool. Now, having said all that, basically what you can do using this tool is basically anything you can do in COMSOL. You can add any of the physics, you can add in anything that you want, but then you can restrict it by having only certain inputs to be put in. You could also add error messages. So if, say, you put in a negative length, it'll say, oops, that's a negative number. So you the modeling expert can actually design the error messages as they come out. You can also put in tooltips. So in other words, if somebody's hovering over an input box, they can actually see in advance, oh, this number needs to be between 1.2 and 1.3, something like that. It also has access to put up help files. So you can, within your app itself, you can have a little question mark button that you could press the help button, and up will pop a PDF help or other contextual help as well. And so the main thrust I'm getting at here is that the modeling expert knows what makes sense to put in and what doesn't make sense. What we've done using the application builder is empower that expert to then transfer that knowledge into an app, and design error messages, design tooltips to let the people know on the other side who are actually using it, who might not be modeling experts, that no, you can't put a complex number here, or no, this length is too big. That kind of thing will pop up. And also, together with the error messages, you can also design those as well. So that's the idea behind the application builder. Is really it's an empowerment thing. I mean, I think one thing that people, simulation experts, sometimes get a little bit emotional about is that, oh, this is my turf, this is my place. I want to have my simulation. No one should touch my simulation. But if we can empower them by using things like templates and like applications, it actually lets them put little guardrails there so that people could say, okay, this is what I should be doing with my simulation. And I think then the simulation expert becomes empowered, and actually their influence is widened, possibly exponentially, depending on how many people wind up using their devices. So that's my little spiel about what we can do with templates, aka applications.
Very good, gentlemen. Here's the challenging part. We probably want to spend about only 6 minutes so that we can hit the Q&A at the right time to address questions. So I have 3 more questions for each of you. If you spend about 2 minutes each, that'll be great. I do all the maths here. So let me call you in first, Joe. Joe, your thoughts on how to make simulation more accessible to the non-experts, and you may also bring up the generative design as well if you feel like this is relevant now.
Okay, let's see if I can stop talking in 2 minutes. That's not that easy for me. Once I get going, I just keep going. So beyond, the ease of use and all that, there's some key ingredients that you have to have in order to be successful with simulation on the design level or analysis level. One, CAD connectivity. Make sure that your CAD updates, that there's a complete link between your CAD and your FEA. All these great things that have evolved over time, like automatic assembly modeling, understanding when there's an adhesive or a connection of a certain type of bolt or anything like that. Everything that's evolved from detailed analysts over time, make sure that that's part of the system. Shared material libraries. Don't have the capability of using something that you're just making up. So all of that stuff together, plus having a unified interface, having a purchasing model that is able to stack everything into one thing. Security and feature upgrades are all consistent. Communication, reduce data transfer and problems in translation. All that stuff is important. Last thing, of course, you got to have speed. You got to be able to run 1,000 different simulations parametrically overnight, or if you're wasting time for a week waiting for some type of crash model to finish, your company's not getting where they want to go. Cloud compute now on the platform is the way to go. You want to work with a partner who understands all this stuff. We're a partner that has the CAD and the simulation capability, custom training courses, mentorship, methodology development, the whole 9 yards. And am I at 2 minutes? I'll leave it at that.
Thank you very much. Sorry to make you rush through things. Yeah,
that's fine.
All right. Mark, what about your thoughts? What's the better approach, by the way? Is it to teach the designers to learn more complicated simulation? Is it to make the UIs simpler? What are your thoughts?
So I'm going to go back to Denso, and this quote that you're seeing on the screen now is from Denso, and I think we showed this previously. And I've seen this played out at other customers as well. But designers can expect to improve their design skills by running CAE and investigating better designs by themselves. And a fast and easy to use simulation environment can really make a significant impact in the overall design cycles and performance of the products. So providing a simulation environment that is part and parcel with the designer's CAD environment is really key too. You want to keep that designer comfortable with the CAE tools like he is with the CAD tools. And Denso, their use of our templates concept, they're pointing to 20 to 80% process time savings, which, you then think about a single iteration, and the time savings that you have there just means that you can do more CAD and CAE iterations to get a better design. So I really do believe that the simulation automation enablers are the appropriate next step towards broadening the FEA usage among designers. And then as the designer becomes more familiar with the CAE processes and methods, the templates become less important as learning tools and become more important as automations to the CAE model build. So they're just able to make the CAE models faster. And then if the designer is becoming comfortable with the use of the simple simulation tools, then they could consider taking more advanced training in CAE methods that are pertinent to their everyday work.
All right. Let me go ahead and call on David for one more question. In the meantime, Mark and Joe, I would really appreciate it if you can now start looking at the questions that have come in from the audience and queue up the one that you'd like to address to the top of the queue. So let me go to David for now. David, both you and Mark have shown applications and templates. Do you feel like in the future there might be a market where the experts simply produce these templates and sell them in some sort of an online marketplace where sort of like a pay per usage model? Do you see that as a future?
Yeah, Sure. In fact, we have people doing that. That would be, that would be more for a situation like you might have for instance, a consultant that's using a software package that they want to then produce an app for a customer, and then the output would be that. But frankly, there's also possibilities for new software companies to arise out of these things. We think about our stuff being new, but really we're actually using other software, right? We're using Visual C++ or whatever to build our software. Somebody's going to use our softwares to build other software. So that's just the nature of software. It eventually will be in the infrastructure of what's going on. But I'd like to mention a little bit more just about this idea of broadening the impact of FEA, and I think it's really a great question. And the question is people, right? I mean, we have an organization. You might have the experts, and then you have the design engineers, like I mentioned, and even people on the factory floor. Now, we've been focusing mostly on getting from the highest pillar here to the second highest pillar, but there's also a lot of engineers that actually will never use simulation itself, but can benefit from simulation. Not only that, they can also use that simulation, their results to go back to the simulation people, and this is things like validation and verification, to help them create better models. So there is a kind of a symbiosis here between them. And so we've added a new aspect to our product called the Model Manager. I haven't mentioned it much, and I won't spend too much time on it, but just to mention that we have this new tool that is basically a simulation data management tool that allows you to it has version control, access control, but also lets you associate data. So you can imagine somebody on the factory floor has this new set of experimental data they want to share with the simulation expert. They can do that through something like the Model Manager. Or a design engineer comes up with a new CAD design. They could also use the Model Manager to share that with the simulation expert. So that's the idea. I mean, again, these are things that we're working towards, and we're broadening out. It's a process, but I think we're getting there, and I think there's a lot of hope for the future with the democratization of simulation, making it more a part of what people are doing out there. I just mentioned one little quick thing. I'm getting my landscaping redone, and they have these beautiful new lights put in. But of course, the worker works during the day, and he can't tell what it looks like at night. And I said, wouldn't it be cool if we had a simulation tool that the guy could use his iPad for, put in where he's going to put those things, and we could get a visualization of what it is, what it would look like at night. Now, we're not quite there yet. But maybe given a few more years, we could have those kind of type of simulations done on the fly, and give access to more and more people.
I think interior decorators would kill for that kind of definitely. Thank you, David.
We do have a Revit add-on that you can. Oh, hey, by the way, I should mention one other thing, just real quick. We have 3 great user stories referring to these apps or these templates at our website. So Volkswagen, Amgen, and a company called Illinois Toolworks, which have some really cool examples of using apps within an organization. So not just theoretical, it's practical.
Very good. Let's move into Q&A and take as many questions as possible. David, you haven't had a chance to, so if you can go take a look at the questions, and if you like some, hit high so that it comes to the top of the queue. Let's take the first one here. Let's see here. Nobody I know want a template or an every manager wants results, not apps. What management wants is a method to iterate models, design products quicker. App template don't seem to serve this purpose. Okay, so that's one opinion. Maybe let's see if any of you want to rebut that. So let me go to Mark first, because Mark, what are your thoughts about that?
Yeah, I think that's kind of that's exactly what our templates are trying to address, is the to quickly build and iterate on these CAE analyses as the design progresses. I've seen companies define templates that are specific to subassemblies on their products, and and the template is more defined based on the characteristic of the geometry. Is it a thin wall part? Can I mid surface it? Is it something that needs to be solid meshed and so on? And then they build their standard modeling practices into the templates, and let the template build the model initially, and then eventually the user's going to have to, of course, jump in there and maybe make some corrections. But the templates are there to speed up the process, and it might not be 100% all the time, but that's exactly what they're intended to do, is allow you to do more iterations.
Okay, all right. So, David, this question probably is relevant to you as well, even though you call it application. We're talking about the same thing.
Yep.
Would you like to chime in on this?
Yeah, absolutely. Yeah, so, I like the attitude, and I think it's true. A lot of managers, especially non-technical managers, they don't want, to use the software. They just want to have results. And we actually just had a great user presentation by a guy at Nissan at one of our events that we were holding, where he showed 3 graphs that he said basically changed the budgeting at a budget meeting. He basically showed a couple of graphs. The manager's like, okay, well, that makes sense. Now let's invest in this design change that they were talking about. And so the point of it is not to get managers to use the software, but it's to get more people to use the software so that the results can then be aggregated and honed toward making somebody like a manager make a decision that would be beneficial to the product. And so and that's why I said, in COMSOL's view, our goal is not just to have to support those that are going to be using simulation, but also those who won't be using it. I mean, there's guys on the factory floor that are actually building something. They don't really want to look at simulation, but the results that simulation they can give can impact their work. Same thing for a manager. And so that's the idea, is that we want to not only have tools to that create better simulations, but also have ways of managing the data that's generated from those simulations to be used in the most impactful way. So that's what I would say about that.
All right, very good. Joe, we may have time for one more question. Is there any question that you see in the list that you'd like to address live? If so, would you mind reading it out and then give us your response, please?
I thought, did someone ask something about, well, how can we contain the cost of simulation tools because of with all the acquisitions and consolidation?
Yeah. There is indeed. Yeah. Let me read that question very quickly. Acquisitions and consolidations have created better, bigger, more expensive tools. But in general, for people who don't work at NASA or GE or GM, how do you make simulation affordable? And your response is?
Well, I would say the first thing is, if you're a company with objectives to minimize warranties, you're going to want to know about problems early on. So if you're not using CAE, then you might have a problem. As far as the increased cost, there's a lot of with Dassault products. There's all kinds of different licensing models now. With the cloud, especially, you can go on a credit consumption basis. Use pay-as-you-go, so that you don't have to invest, your whole budget for the year on things, and be able to work within your peaks and valleys. But the idea that simulation is too expensive for a company to bring in, and you're only able to do it if you're NASA, that I think is hopefully is not a primary thought in most people looking to use CAE nowadays.
All right. Very good. Thank you very much, gentlemen. I'm sorry that we cannot go through more questions, but we'll make sure that all of you get the list of the questions so you can actually respond to them in writing. To the audience, I appreciate you spending your time with us, and to all our wonderful panelists for sharing and doing demo and breaking down the pros and cons. I'm grateful for your help. To the invisible production manager, Steve Paul, who works behind the scenes to make everything go smoothly. I also want to express my thanks to you, Ernest, as well. This episode has been sponsored by CATI, COMSOL, and Siemens. So until next episode, everyone, thank you very much. I'll see you again soon.
Thanks, everybody.
Thank you. Bye.